Okay, I thought we proceed a little bit on the lecture because this morning we were a bit cut short on the lecture. And anyway, today would have been a shorter lecture allotment and a bit longer, so I think we can make that work. And also, I don't want to hold you back from getting to know about the Ampere's law that we are covering right now. So I would do a bit then, and then I switch to the tutorial after we have done that. So then I think that might be good. Then you can familiarize yourself already now with that concept of this Ampere's law, because that will be relevant. And next week when we then get towards Maxwell's equation, and also because I think we should, that has been a bit interrupted today. So we have seen here earlier that these are two types of fields that we are considering. The electrostatic field, and on the other hand, on the magnetic side, we have here the B field is a magnetic induction, or the magnetic flux density. By the way, if you look at also how the electric force is given to you, you know that is the force you have on the one hand by Q and the electric field, but then you have also the Lorentz contribution, which is given to you by the cross product of the velocity and the magnetic induction, or the magnetic flux density here, times the charge. So you have two components here, but you see what is the force component here is basically the electric field. I mean, you know that we also have the electric displacement field, and it's directly related through the permittivity. This is this epsilon E. But I want to stress that conceptually these are different things, because this here is a flux density and this is not. But you also see that what is responsible for the force is the electric field. I mean, you cannot totally separate them because they're directly related. But if you're thinking of a force term, you're thinking of the electric field. And here also, what is giving you the force in the magnetic field, that is this magnetic induction. But interestingly, this here actually is a flux quantity, because the D here, the electric flux density, if you think about the units, then you have here ampere seconds per square meter per area. And here you have volt seconds per area. So if you look at the sources of these fields, that would be the E field and the B field, then we have said you can have here monopoles or dipoles in the E field. So you have points from where the field lines originate or where they end. So these are your sources. However, on the B field, you also have something which is generating them. But that is not a source in the mathematical sense, because your field lines, because your field lines are closed. They're not ending or starting anywhere, but they are closed. And for that reason, what this denotes is that the magnetic field is a source-free field. It's a solenoidal field. Of course, you can have regions in the electric fields where you have no sources, but somewhere you have a source for your electric field. And somewhere you will have the situation that when you apply Gauss's law, that this surface integral over a closed volume will give you some charge contribution. And these are the sources. The charges are sources. So now, you know, if you have take a magnet, if you have even a solid magnet, if you're taking a magnet with a north and south pole, you break it into two, you get two pieces of magnets, and then they still have again a north and south pole, right? You cannot separate them. No matter how small you break it down, it will be always a source and a north and the south pole. And that is, you always have dipoles, magnetics, where the magnetic field lines from the if you, for example, take such a permanent magnet, when you see what is generating them, then you have a north and south pole, but these lines are also always closed. So it's a solenoidal field. That means the divergence, or also in integral form, the surface integral over the flux of B is vanishing always. Also, if you draw your surface, your reference, your control volume somewhere here, it will be always vanishing. So this is important to notice. By the way, then these also are already some of your Maxwell's equation. This is part of the set that describes you the interaction of the electric and magnetic field. And the next one that we also need is the Ampere law. Actually, that will later need to be expanded for the Maxwell equation, but I want to tell you now what Ampere's law is, because right now we have stated, yeah, we see that if we saw that video and you had a wire where there was current flowing and you could see that the magnetic needle of the compass is deviated, but we haven't given any well, in some way you cannot really give justification for it, but we have not brought that into a closer formulation. How is this magnetic field related to this current? And this, of course, is based on observation and experiment, and then there could be a formulation derived that expresses this physical phenomena, which is in the end an effect of nature that is not really open to any reasoning. This is this is a law that matches our observations and experiences that we can derive to describe that phenomena. And what we're looking now is Ampere's circuital law, so the quasi-stationary version. So we have static B field. So this is magnetic induction, or same way to say is magnetic flux density here. So they are generated by moving electric charges. So moving electric charges, either obviously currents, or they can also stem from current densities that you have seen in this demonstration in this video that I showed you earlier at the introduction for the chapter 3. And we find that there's a constituting relation between the magnetic field, the magnetic induction that you obtain, and the current that is flowing in the wire. And we also know that we have just seen in this previous chapter this morning in 3.4, that the divergence of B is 0. Yes. Thank you. And why is it not showing here? Looks like it's connected. Not sure what happened now. This is very strange. Let me get it a quick restart. Very strange. Oh, I'm sorry, so that is not working. Whatever problem is, or was, I think now it might be even working again. I don't know why. Okay, so sorry for the lengthy interruption. So the divergence of B is 0, and in the global version, that means on the microscopic view, we take the integral formulation that reminds you, of course, of Gauss's law, but this is different and only in the sense that now it is not applied to the electric flux density, but it is applied to the magnetic field. And because we have no magnetic charges, this is always 0. This is source free. And that means also the term mathematically, it means it's a solenoidal field. So for the B field, we have the generating quantity is not the charge, it is electric current. So that is a major difference. The electric current is the generating quantity, and this is um, not a source in the mathematical sense. Of course, uh, if you being more colloquial, you could say that yeah, I mean something which generates a field, but strictly speaking, it is not a source because it's a solenoidal field. This electric current is a generating quantity for the magnetic field, but this is no source in the mathematical sense. So the field lines don't start or end there at this source because it is not a source. So if you compare electrostatic, you have your charge Q, and you have then an electric field which is originating from that charge point, from this point charge. You have your electric field. You can give volume into a control volume that would be V, and it would have a closed surface. But that is for electrostatic. So how does it look for the B field? We have just named it. It is electric current. So you can calculate B field, and the basis for that, to sketch that for you, is you have here wire. There's some current flowing in this wire, and then you have some magnetic field, which I make here. This is black lines, and this is our uh, shall be the magnetic induction here. And we want to prescribe now a control area. You know, this far when we looked at the Gauss law, we had a control volume. Now we go for a control area. And this area is here depicted in red. That shall be our control area. And this area has also some thing that is prescribing the limitation of the area. So for the volume, we had an enclosing surface, and for the area, we have an enclosing path or curve. And that we denote with this dA here. This is a closed curve around A. Now we can generalize that because we are interested in the local variation or variant of local formulations. We have seen that the current is actually more some global quantity that you obtain by integrating. And what do you integrate over? Well, you integrate over the moving, you integrate over a area and look what are the charges moving through this area. So we are generalizing it for moving charge densities. Charge density we denote with rho, and that means we are interested in our current density, which is the charge, space charge density times the velocity field here. That is our current distribution, or rather the current density here. We are working with current densities. And now instead of having here just this single line with a wire, we actually have here, if we depict that, these many arrows which denoting our current density field. And then we prescribe again a control area A, like in the picture above. And we have also now a closed curve that is the border of the control area. So your current, of course, is then obtained by integrating over this area and integrating over that current density. So the area, if you look at the orientation, this is your normal vector, and the area is right-handed oriented. You know, area A. Area A is right-handed oriented. What does it mean, right-hand oriented? That means if you take the area, this control area, you take that, and now, of course, you have the choice of what is your normal. You could put it upward, but you could also have it point downward. But wherever you put it, if you apply the right-hand rule, your thumb is basically aligning with the normal vector, then your fingers are giving you the direction you will go around at the boundary curve. Hence, the orientation you follow on this curve, well, I wanted to draw that in the lower one because there we have drawn the normal vector, is in this fashion. So the curve C is oriented in counterclockwise direction. That is what right-hand oriented means. Curve C is oriented in counterclockwise direction. And n, the vector n is our normal vector that is here now in upward direction. And of course, you can make it downward, then just follow the right hand rule. So to say, the thumb of the right hand aligns with our normal vector. And n is a normal vector of A. The normal vector is, as usual, normalized to 1. So now we can introduce also a magnetic field strength. But let us first see here this relation between the magnetic induction and the current. So we have defined a control area which has an enclosing curve that is this is the outer line here. This is the enclosing curve that we define. And now we have some current that is flowing through this control area. Some current or some current density. It is penetrating the area A. And then we can establish a relation between the curve integral over the B field, so along a line, and the current that is penetrating through this control area. And that is the Ampere law. So the steps are as follows. We define the control area with an enclosing curve. So that is the curve that runs at the edge of the area, or how we would say that's a boundary curve of that area. At the enclosing curve that we denote with C, but this is a enclosing path, and like you see the analogy for the surface, we have an enclosing area that is denoted with this dV, but here we have an area, so we have an enclosing curve. So in an appropriate way, so what that means, you will see then in the examples, in an appropriate way for a given problem. So that usually means we have it around the currents, the enclosing surface, so that we want the current flowing through this control area. And then we consider the given current that we obtain by, well, if it's given as a current, or we obtain it by the current density and integrating over the control area, over the current density. So consider then the given current or the current density, which is penetrating the area and you know that the current is obtained by taking the area integral over the area on the current density. That is how you obtain your current. And the very interesting part is now the relation here, and that you have to accept because it is a law, physical, that is based on empirical considerations. So we have a relation between the current and the magnetic induction. And the relation is such. So you have the integral over the curve, which is a closed curve around the control area. And you integrate along this curve the B field. So you see the dot product here. So the B field component that aligns with this vectorial differential line element dr. And this integral gives you the value of the current times some constant, which is here written as mu 0 or mu naught. And of course, this current, we just stated that, is actually the current density integrated over the control area. Isn't that a nice formula? So this is your, if you look at the written note, it is your equation 321. And this constant, this is a mu, this is a Greek letter mu. You pronounce it something like mu or the like mu or MEW mu. It's Greek. Mu. And here, this is your control area again. But mind, this is not a closed surface like we had in the Gauss law. This is just a regular area. If it was closed, we wouldn't have that closed curve for it, right? For the closed area, for the closed surface, we don't have a boundary. This is not a closed surface. As we had seen earlier, this is not a closed surface around a volume. So we have introduced now this parameter mu. And what is this parameter called? So this is kind of in analogy, we had in the Coulomb law, we had this permittivity. That was a material parameter. Now also here we have a material parameter. This mu naught or mu zero here, this is called the permeability. Permeability, or you can also call it the magnetic field constant. The permeability or magnetic field constant of vacuum. And what is the value of that? This is 4 pi times 10 to the minus 7 ohm second is a unit per meter. This is in analogy to the permittivity, which is the permittivity of vacuum. If you are now in a material, then you have to adjust this permeability. You account with, or you account by using the relative permeability denoted as mu sub r. This is also an analogy to what you have for the permittivity. There you also have an epsilon sub r, and here for the permeability, you also have a relative permeability. So you have your mu r here, and this is for this you need for the B field in material, and also this is your free space permeability. So now we had this first relation between the magnetic induction and the current. So if we have it now in material, then we make the adjustment for that, and that looks as such that we now again take the integral over the curve, closed integral, for the curve enclosing basically the control area over the B field. Let's make some nicer arrows here. And that would be then mu naught times mu relative times current through this control area, or if you write it with the current density, it would be mu naught times mu r integral over the area, the control area, over the current density, and that would be then also, again, you can write that as just mu times I, and then you basically take the absolute permeability here. This is absolute permeability. So you have to consider then this is basically the product of, as you see earlier in that line here, of mu naught and mu relative. That is the equation 323. And different to the previous one, that is what you use in material. And now we introduce a second field quantity. This is also in analogy to what we had in the electrostatic. We had the E field and the B field, the E field and the D field, the electric field and the displacement field, the electric displacement field. Now we introduce the magnetic field strengths. And this is denoted with an H. And now we define the H field to be 1 over mu times the B field. So magnetic field strength is 1 divided by the permeability, the magnetic induction or the magnetic flux density. Or the other way, you can write the B field by taking permeability times the field strength. Remember what we had in electrostatic. This is just an analogy. In electrostatic, we had something similar. We had the D field, the dielectric flux density is given by epsilon naught epsilon r, the electric field, or you can also write it just as, get the absolute permittivity as a product of the vacuum permittivity, so the dielectric constant in vacuum times the relative one, the E field. This is your D field. And here, this E field, remember, that is a force field. And you remember the D field, on the other hand, that was related. I mean, they're also interrelated, but this we look at really when we are looking at the generating quantities of the field. That means for the charges. Yeah, you agree with that? And if you, however, compare that now, we have the magnetic field strength, H, and we have the magnetic induction. It is that the field strength is actually related to the generating quantity or quantities. That would be either your current density or your current as a whole. And the B field is actually the force field that we have seen if you look at the Lorentz force, that you have there Q times E for the electrostatic force component. So the E field is directly related to the force. But you also had the Lorentz force, which is Q times the cross product of voltage and the magnetic induction. So the B field is your force field in the magnetic, and it contains the impact of the material. That is also like that in the electrostatic case, your electric field contains your material properties. And that gives us now Ampere's law. You can also leave that accent away. So you have the closed curve or contour integral over the magnetic force field that we just introduced, and that is the current as a function of the area. So what have we done here? We have, if you remember, on the one hand, if you go for the Coulomb law, you have a force which is proportional. We said the force between charges is proportional to this permittivity. Yeah, it is also proportional to the charges, the product of the charges, and to the R square. But you see that the force here is a function. I mean, the material properties are accounted already for in the force. So force, if you have a different material, your force will be different. And when you introduce the D field, you're taking out this by multiplying with the permittivity. But the D field here is a flux quantity. And if you compare it now to the magnetic fields, it is that your B field, your magnetic induction, is actually the flux quantity, but it is actually the one that is responsible for the force. So that is your force term. And for the magnetic field strength, you have removed the material property again by dividing it through the permeability. And it tells you something about your generating term of the E field. You have removed the property of the material in that. So let's maybe break here for the lecture and then switch to the tutorial. But then you can already a bit think about that, of this relation, because I think this is quite important. And I will revisit that also on Monday when we continue. I'm also not fully done, but almost with this part 3.5. But maybe let's have 5 minutes break. And then let's do the tutorial. Or do you want no break? Because break or no break? Break? Okay.
A bit long on the chapter 3. So basically, from my understanding, chapter 1 is just talking about Lorentz force, which is when a charge is in magnetic field, they experience the force, which is called the Lorentz force, and that's how
If a moving charge, yeah. It has to
moving
be
charge,
moving
yeah.
charge, yeah.
Correct. So when it is when it is perpendicular, it will start to spin. Perpendicular to
So the charge, as far as it moves perpendicular to the magnetic field, it will experience this Lorentz force.
which is what causes it to go.
And if the field is uniform and extended far enough, so that, for example, it could also be that the particle enters and then it will be deflected by the Lorentz force, but it will be moving so fast that it
needs to
is
be big enough for it to start
that it
curving.
might leave the field already. But if the field is extended far enough, then it
Start to swirl.
make a turn. It will turn around.
We turn or we spiral.
That depends. If it has a component in the force vector that is aligned with the B field, then it will make this helical
So it
movement.
depends on the force.
Otherwise, if it is has just a velocity perpendicular to the magnetic field, it will just go in one circle. And that is also because there is no energy added to the particle or taken away, because that force of the Lorentz force, that is always acting perpendicular to the direction of movement of the force. So that of the particle, it is always perpendicular to the motion of the direction of motion of the particle. So if you look at the integral for the work that possibly could be done, you see there is no work done, because the work integral is force over the times the path. I mean, but there's no force component aligned with the path.
The charge and the electric field.
So here you combine both. You combine the electrostatic and the Lorentz force. Sometimes the whole thing is also called Lorentz force.
So that's why when you integrate it, you'll be technically busy for work.
Because you see the velocity is here dr dt, and you have here whatever is in here comes out of this cross product will be a vector that is perpendicular to that and to that component. But if it is perpendicular to R, then whatever is taken then as a dot product with the line element dr here, that will vanishing, because if you have anything here in the cross product and then still take an inner product with that, that will
Oh,
be
it's like doing
vanishing.
nothing,
Hmm?
because it's like
This term, you know, will be zero, just because you know this vector and this you're taking a cross product, so the resulting vector of this cross product will be perpendicular both to this vector and it will be perpendicular to this vector. But if this vector is perpendicular, the resulting vector is perpendicular to this vectorial element of the line element,
then this will end up being parallel.
then this whatever comes out here is perpendicular to this. And if you take here this inner product, then it's vanishing, it's becoming zero.
Wait, but isn't the reason is there's a force is because it's perpendicular?
Yeah?
You want to try?
Oh, thank you.
It's spicy, by the way.
Thank you. Oh, it looks like. Thank you, Trip. Very nice, yeah. So let's proceed a bit with the tutorial because we don't have actually so much time even anymore. So let's look at this example. You know, we had earlier yesterday in the tutorial, we were looking at this capacitor. And can you appreciate why we come up with this equivalent circuit? Because you can think of this structure, you can basically make a cut here through, and you see that both are having the properties of a capacitor, and it is like setting two capacitors in parallel. This is just like what we did in the lecture. And then we see that this equivalent circuit, lumped circuit elements are actually very well describing our setup. And you can use here basically a physical realization of a capacitor, and from the geometrical and parameter properties derive here lumped circuit element the description that you can use in some circuit simulator. So if you have any more intricate geometry, then you can boil it down or bring it down to this simple description of a lumped element in a circuit model. And that, of course, helps you a lot if you want to do any further higher level computation or assessment of any circuit. So how does it look when you determine capacitor of some arrangement where some capacitors are put in parallel or in series? Have you done these kind of circuits where you derive some equivalent capacitance from setup like this? Yeah? Well, let's look at that example. This is question number 11. You can find in your short question collection in the tutorial. So we know that if you have a serial connection of a capacitor, you have a capacitor C1 and C2 in series, then that total capacitor will be C1 times C2 over C1 plus C2, yeah? So that is basically our C serial, and that is equivalent to the series connection of C1 and C2. This is the formula. So if you look at the problem that we have here, we have first on the leftmost side 2 capacitors in series. And on the right-hand side, we have here in the top, let's put it, you can say that on the top we have a parallel connection of two capacitors, and these two parallel are then in series with a third one. And then you have here at the bottom a series connection of another two capacitors in parallel. And you have given the capacitor values. This is actually already the value, right? They all have the same value, C. So basically what you see then is that you have up here a parallel connection. So the total capacitor value of this parallel connection gives you 2C. You have a series connection on this side of capacitor C with capacitor C. That gives you 1/2 C, yeah? If you have here C1 is equal to C and C2 is equal to C, then you have at the top, it says C square, and at the denominator you have 2 divided by 2C. So C square divided by 2C is C1/2. And now you have here on the left-hand side, if you also take this one into account, then you have another capacitance. So you have this a series connection of one capacitor with the value 2C, and this has, of course, the value C. So that would be 2C times C divided by 2C plus C. That would be 2C squared divided by 3C. That gives you 2/3 C. So you have here 2/3 C for these two capacitors. Now you go ahead and take the whole thing here, the whole top thing here. That is a parallel connection of this one and this one, yeah? So you have 1/2 C plus 2/3 C that you bring onto the same denominator. That gives you 3/6 C plus 4/6 C. That would give you 7/6 C, right? And then you have here another parallel connection that would give you 2C, and then you just add the C. To add the C total, you take a series connection again of what is 2C here and 7/6C here. So that would be 7/6C times 2C divided by 7/6C plus 2C. That gives you 14/6C square divided by 2 times 6. This gives you 12 plus 7. This is 19/6C. And sorry, I think I should write this more neatly because this is a 4 divided by C here. So that gives you 14/19 times C. Agree? So I have some more material for the capacitor, but I think maybe I'll maybe if we have some more time, I will revisit that. But maybe let's make the short question 12, and then I will go to the. Let's take both of those. So remember what we had in the lecture. We had these two capacitors, which have which are parallel. Well, they're more. I would rather say side by side. Yeah, but actually, this is just what we have done in the lecture. Maybe let me get to that, to this problem right away. I think this is better. So, and I hope I can start a bit on the current also today. So you have a perfect plate capacitor and it has been charged in a free space with a charge Q at a voltage U. Then a dielectric material with relative permittivity is filled between the capacitor plates. What is the change of the electric energy stored in the capacitor? If A, the voltage between the plate is kept constant, and B, if the charge on the plates is constant. So there are two different ways you can approach it. First, you are keeping, it makes a difference if you keep the charge or the voltage constant. Let's look at that. So we have a plate capacitor which is charged with Q at the voltage U. That is a first step. So how does this parallel plate capacitor look like? You have one plate here, one plate here. You have, so these are your two electrodes and they're connected somehow so that I can apply a charge, a voltage here. And in consequence of applying this voltage, you will add some charges here on the electrodes. This will be the charge, and on the opposite, you will have the other type of charge that would be minus here. And then you have some material that is, in this case, I think, filled in at a later point of time. So a material which had well, it has some relative permeability ER. And so that is the second thing. You bring in that dielectric material with a relative permittivity. So what is the electric energy that you have? We said in the parallel plate capacitor, but also actually in general in any capacitor, the electric energy that you have is 1/2 C times U square, or you can also write it as 1/2 Q times U, simply because C is give the relation between Q and U. So you insert here for C Q divided by U. So you will have 1/2 Q times U, or the other way you can express it is you replace the U by Q over C, then you would have Q squared over C. So this is the energy in your capacitor. And for the parallel plate capacitor specifically, so the above is general true for any capacitor, but for the parallel plate capacitor, the capacitance is E naught times ER times A over D. So in the first instance, you have a capacitance where you have no special dielectric inserted. That would give you a capacitance of E naught times 1. The relative permittivity is just 1 times A over D. A is, of course, the area of the plate. D here is the separation of the plates. And in the second case, you insert then this dielectric material and your permittivity, the relative is 2. So that would be your capacity with dielectric material ER. And the question was now the voltage between the plates is kept constant. So in the first problem, U is constant, and we say that is U0. So the electric energy is 1/2 times C times U square. So if we keep the U constant, then we have in the scenario 1, the electric energy in the scenario 1, we have 1/2 times E naught times A over D. This is our capacitance times the voltage squared, right? So basically, you're just taking here the formula for the electric energy on the capacitor in general. You know that U is the quantity that is being enforced on the capacitor. Then you need to know the capacitance, and this is the capacitance in the first scenario. So that would be C1, yeah? In the second scenario, you also have 1/2 E naught, but now you have times 2. This is your ER times A over D times U naught squared. This is 1/2 C2 times U naught squared. But if you compare that, you see that this is now twice as large because this doesn't look like an R. Let me write that again. Because your relative permittivity has changed from 1 to 2. Now, as a consequence, you're also storing twice the energy. So by changing your dielectric material with one that has a higher permittivity, you can store more energy in the capacitor, which otherwise has the same geometrical properties. You just have modified the material parameters. And in the second case, we have the charge constant, and that is Q0. So the electric energy now is given by 1/2 Q0 squared over C2. You see, we can express the energy in different ways in terms of the voltage or in terms of the charge. And the question is, which quantity are we enforcing? In the first scenario, we have kept the capacitor connected to the voltage source. And first, when there was no dielectric material inserted, it was charged up and it was then containing the energy WEL1. But then we inserted this dielectric, but we kept the voltage source connected. So it was increasing the capacitance, not the capacitance, it was increasing the electric energy that it is stored. The capacitance actually, it was also increasing, and accordingly, that is the C2. So if you look at it, we also increase the capacitance, but the important thing is also that the energy stored is also scaled up. So that goes in the end, the energy and the capacitance in that circumstance goes hand in hand. But in the second scenario, now we keep our charge constant. So the electric energy is 1/2 Q naught squared. And for the second scenario where we have inserted that dielectric, it is then 1/2 Q squared over C2. And remember, the C2 is twice C1. So we have this energy is 1/2 Q naught squared 2 times C1 is 1/2 electric energy 1. And in the first case, we had the energy is electric 1 is 1/2 Q naught squared over C1. So you have to appreciate the difference is in the first scenario, we insert that dielectric material, but we keep the charge, we keep the voltage between the electrodes constant. So the charge will then adjust based on the modified capacitance and the voltage is still fixed. And in the second scenario, we basically have charged up the capacitor when there was no dielectric material inserted. By applying a voltage, then we disconnect the voltage source and then we insert the dielectric material. Now let's look at the problem, the short question 14, and we really get into the stationary currents here. So you have here this U-shaped conductor, and it carries a uniform current density, and there's also no current outside that conductor. So you have a current flowing in here, and that same current density here is also flowing back in the other. I mean, it's still in the same connector, but it makes a turnaround, and so it keeps flowing. So you have here on these two sections the same current density. So what is the meaning of the term uniform current density? That means uniform current density means that the current density is here constant all over in space, everywhere in the conductor, actually, in this specific example, but in general, it is uniform. That means magnitude is constant in space, or respectively here in the conductor. So if you look at the conductor, that means this is the cross section of your conductor. If you describe that by the field lines, they are everywhere of the same magnitude. They are not decaying, for example, towards the outside or inside of the conductor. Then what is the total current flowing through the area? Well, the total current, you can see here right away, it is actually zero because your magnitude of the current density in the conductor is everywhere constant. So whatever flows through this area here at the top flows also back in the lower part here. So the inflow and the outflow are identical. The inflow and outflow of current is the same. And what will change with respect to the total current I if the current density in the conductor is not uniform but still stationary? So C, you have this situation that it is stationary but not uniform. Stationary means it is constant over time. So if you look at the cross section of your conductor again, then your current could like that, your current density could look like that. That, for example, you have a high velocity for your charges, or it doesn't have to be velocity, it can be a higher number of carriers at the outside, but in the end you have it can be a variation of the density, and more likely is it also. You have here a larger magnitude of the current density vector outside than inside of the conductor. So still, it is now not uniform, yet still we will have inflow equal to outflow because the magnitude of the current density in the upper part, in the wire crossing, intersecting with the control area at the top, and the lower will be still the same. Just within the wire, you will have a variation. Oh, how do I get them separated again? I'm sorry. It is short question number 15, if you want to take a look at it. Perfect. Short question number 15. Assume that several species of charge carriers contribute to the current flow in the conductor. What is the impact of the specific charge of the carriers on the electric conductivity? Possible answer is none. Possible answer B is only electrons contribute to the electric conductor. So the electric conductivity, that is sigma. answer C, the algebraic sign of the specific charge is important. And number D, only the absolute value of the specific charge is relevant. So the sigma, if you have a different number of different type of species, you remember that would be adding up over the different species from 1 to k, and they have here different charge per carrier. This is an alpha, different charge, and they have a different particle density, and they will have different carrier mobility. So what is the impact of the specific charge? Well, none is not correct. Only electrons contribute to the electric conductivity. No, that is also not correct. You can have different charge particles than just the electron that can move. The algebraic sign of the specific charge is important. Now you see actually that the conductivity depends on the absolute value of the charge, and only the absolute value of the specific charge is relevant. Yeah, that would be then correct. So Q sub alpha is a specific charge of the carrier alpha. So D is correct. And remember, the current density is given then by sigma times the electric field. Let's go to question number 16. And that asks which of the combinations, so you have here on the top row, you have different charge carrier, sorry, and in the bottom, you have different charge carrier densities, n of x plotted. And in the top row, you have different conductivities plotted, and which one could go hand in hand. So assume that only one species of charge causes the electric current and assume a constant carrier mobility. Give reason for your answer. So this up there is a function of sigma of x, and this is the variation of your carrier density as a function of x. So this is basically your cut along one axis through some conductor, and so what it goes hand in hand. So you see they qualitatively somehow should match. If you look at the carrier density here, where's my mouse pointer? Yeah, if you look at here at 1, that could go hand in hand with a profile, what you have here up there for the conductivity C. So C and 1 are a possible pair because qualitatively the if you think about, that would be our reasoning, if you think about the sigma as a function of x, that is determined by the absolute value of your charge. It is determined by your particle density, and that is also a function of x. And then it is determined by the carrier mobility. So this here would be a constant because we are also only looking at one species of carriers, and also that mobility would be a constant. So qualitatively, the sigma should follow in its profile the profile of the carrier density. So sigma x should be proportional to the profile of the carrier density. And if you look, 1 goes along with the conductivity profile that you have at C. So that would be one solution. Then 2 would match with A. If you look at 3, that is anywhere a little bit odd, maybe distribution, but that doesn't have any match. If you look at the top for the sigma, and 4, that would also go along with A. So you can match, these are the possible matches between conductivity and carrier density profiles. Then I would like to come to 7.